Okay, so electrostatic is being divided into four main parts. The first one is force, and force we know it's all about Coulomb's law. So Coulomb's law tells us that F is equals to kqq over r squared. So this equation you use it to calculate magnitude. Okay, you use it for magnitude. Then how to determine the direction? Direction is based on the sign conventions of the charge. So when you apply these equations, remember you ignore the negative sign. Okay, when you calculate magnitude, you ignore the sign. This is very crucial. All right. So if you want to determine the directions, okay, the direction, then it is depends on the sign. Okay, depends on the sign. So that is a slight difference between a scalar quantity and a vector quantity. So force is a form of a vector quantity. So it contains a magnitude and also direction. Magnitude being determined by the equations. Direction is based on the sign conventions of the charge. If you have two like charge, then they will repel each other. If you have two unlike charge, they will attract each other. And when it comes to field, there are two types of fields that you have to know. The first one is the field for a point charge, and the second one is the field for a parallel plate. And of course, the definitions of the field is a E equals to F over Q naught, which can be used for both point charge and also a parallel plate. So when it comes to point charge, okay, when it comes to point charge, you use equations E equals to KQ over R squared. And then if you are looking at a parallel plate, okay, parallel plate, then you use equations E equals to delta V over D. And once again, okay, when it comes to electric field, you ignore the sign. Okay, you ignore the sign. And once again, the directions can be determined by using the sign conventions of the charge. If you have a positive charge, directions of the field is pointing outward. If you have a negative charge, then it is going inward. So the ways you determine the sign conventions is slightly different than the force. Field, it depends on just one charge. As long as you have one charge, then you can determine the directions of the field. When it comes to force, you need a minimum of two charges. Okay, you need two charges because you want to see whether they attract each other or they repel each other. So that is force and field, and they are vector quantity. Remember, when it comes to vector quantity, you need the direction. So we have seen what is the potentials yesterday. Okay, so potentials and potentials energy, they are a form of a scalar quantity. Okay, so when we talk about scalar quantity, we ignore the direction. It don't have directions, so you don't have to think what is the direction of the potentials and the potentials energy. Potential it tells you the work done in bringing a charge from infinity to a point inside electric field per unit test charge. Okay, so you have the definition. Remember the definition is a V equals to W. W from where? W from infinity over Q naught. So this is the definition, right? This is the definitions. And potentials, there are a few things that you need to take notes. The first thing is, okay, we have the so-called equipotential surface. Okay, equipotential surface. Now, when it comes to equipotential surface, it tells us that as long as the distance of the point that you are looking at, the destination, okay, the distance between the destination and the point charge, they are the same, then they will have same potentials. Okay, they will have same potentials, they have equal potential. That's why we call it equipotential surface. For example, if you have a point charge, okay, so as long as the distance between point charge and the points that you want, for example, point A here and point B right here, if the R is the same, then the potential would be equal. Okay, if RA equals to RB, then VA is also equals to VB. Because of what? Because V depends on the R. Okay, because V, if you expand equation, you're going to obtain another equations called V equals to KQ over R. And once again, this is for point charge. Okay, this is the equation for point charge. Now, this is if you are looking at just one charge. What if you have more than one charge? Then you have to be careful, all right? In this chapter, there's another two things that can be asked. The first one is what we call total potential. Okay, so total potential, basically you just add up the potential coming from all of the charges. All right, so for example, okay, if you have 2-point charge, then you're just going to add the V1 plus V2. Okay, you add V1 plus V2 if you have 2-point charge. But then there's another thing where we call potential difference. Don't get confused between these two quantity, okay, these two things. So potential difference is that now you have one charge. Okay, you have just 1-point charge, and then you're looking at the difference of potential between 2 points. Okay, so let's see potential difference, a total potential. So for example, total potential, you have a charge Q1, and then you have a charge, okay, you have a charge Q2 right here. Okay, you have charge Q2. So you're looking at total potential, let's say this is point P. So you want to calculate total potential at point P, you calculate the potential coming from charge 1. Okay, calculate the potential coming from charge 1. And then you calculate potentials coming from charge number 2. And then you add them up. That is how you calculate total potential. But when it comes to potential difference, we have just 1 point. Okay, you have just 1-point charge. Let's say this is your point charge. But then you're going to see what happens if you move, for example, you move a test charge, okay, or you travel from one point to the other point. Let's say now you travel from point A to point B. Okay, so you have just 1-point charge, but then you move another item, or you're looking at what is the potential difference between two different points. You're traveling from point A to point B, or you move the test charge from point A to point B. Okay, so let's say now you move it from point A to point B, then potential difference would be delta V is equals to V at point A minus V at point B. But then you're still using the same point charge, which is Q. All right, which is Q. So this one you're going to get KQ over RA minus KQ over RB. So they are using the same Q. Whereas when it comes to the total potential just now, what happens right here is you have different point charge. So KQ1 over R1, okay, and then this is your R1, and then you have another one which is KQ2 over R2. Okay, KQ2 over R2. So that is the difference between total potentials and potential difference. So don't get confused between these two things. All right, students always get confused when it comes to total potentials and potential difference because you guys don't know what is the difference between these two given situations. So total potential, you look at how many charges do you have in the system, and then you add them up. Okay, you add a potential coming from every single charges. If you're looking at potential difference, then you are looking at the difference at two destinations, two given position. All right. So the last one we have a so-called potential energy. Okay, potential energy. Let's say potential energy. Now we have we might have three different type of question. The first one is the energy needed to add a charge into the system. Okay, so like I told you yesterday, if you have a system, initially there's nothing, and then you want to establish a system. Okay, so this is our system, let's say. So initially there's nothing inside the system. So you want to add a charge here. The first charge that you put in the system, you don't need any work done. Okay, no energy is needed to add the first charge into the system. So this one, we have U1 equals 0. Now, if you want to add the second charge into the system, okay, so this is your Q1. So if you want to add a second charge into the system, then you need to do some work to overcome either the repulsive force or the attractive force coming from the first charge. If you want to place it right here. Okay, so if you want to place a second charge right here, then you might need some energy. Okay, and the energy needed for two charges, okay, a system of two charges, we use equations U equals to KQ1 Q2 over R12 if you have a system of two charges. Now, what if you have a system of three charges? Okay, what if you have a system of three charges? Now you want to add in a third charge into the system. Okay, you want to add in the third charge into the system, then you need to calculate another two energy needed. Okay, another energy needed to add in the third charge. Okay, which is the energy needed to overcome the force coming from Q1 and also the energy needed to overcome the force from Q2. So if you have a system of three charges, okay, then the total energy inside the system would be U equals to KQ1 Q2 over R12 plus KQ1 Q3 over R13 plus KQ2 Q3 over R23. So this one is the energy needed to put in the second charge, and then this is the energy needed to put in the third charge. Therefore, all together inside the system now we have this much of energy. Okay, you add them up. Okay, you add them up. So this is from the second charge. This is coming from the third charge that you add into the system. All right, so that sum up everything in chapter 1. So chapter 1, four main category. Okay, you have a force, field, potential energy. And then so we have seen what are all the possible questions that can be asked. Oh yeah, and of course, just now I forgot to mention, when it comes to parallel plates, you have four cases. Okay, you need to know how to solve all four cases. You need to know what happens in all four cases. All right, so I've already mentioned it in a class yesterday. First, you have a static equilibrium or a stationary charge in the system. The second one, you have a charge moving parallel to the field. Third one, you have a charge moving perpendicular to the field, which will give you a parabolic path. And the last one is what we call dynamic equilibrium. So we went through all the details informations in all four cases yesterday. All right, so if you forgot already, make sure to go back to go through the notes again. All right, make sure you go through the notes again. So four cases, I will lead you, and I won't explain it again today. So today I'm just going to give you a brief summary like this one. All right, so now I give you a few minutes to write it down. Maybe I give you until 20 past 10, 4 minutes from now. All right, you can write it down. You can take a screenshot and then go through it. If there's anything that you don't understand, ask now. All right, don't wait until right before the exam. So kalau ada patah paham, anda tanya sekarang. So saya bagi sedikit masa untuk catat. Example 5, now you are given 2-point charges. Q1 equals to positive 0.3 coulombs and Q2 equals to negative 0.4 coulomb. Now you look at the questions. Now you have one positive and one negative charge. One positive, one negative. Now you're looking at potentials. Potential is a scalar quantity. So scalar quantity, you need to take into consideration the negative sign in the charge. Remember, only electric force and electric field, you can ignore the sign of negative charge. When it comes to potentials and potential energy, you need to take into consideration the sign of the charge. Right? So now you have positive 0.3 coulombs and negative 0.4 coulomb. They are separated by a distance of 6 meters as shown in the figure below. Calculate the electric potential at point A. So you want to calculate the potential at point A. Now point A is here. If you look at point A now, point A is being placed in a system of two charges, which means you need to take into consideration the potential coming from both charge. So point A is located at 3 meters from charge Q1. So 3 meters from charge Q1, meaning that it is also 3 meters from charge Q2. All right, now let's see. So you want to calculate potential at point A, VA equals to, okay, you have two charges, Q1 and Q2. So calculate the potential from charge 1 first. So Q1A plus V1A, sorry, and then plus V2A. So potential from 1 and potential from 2. So you need to take into consideration the potential from the both of them. So it is equals to KQ1 over R1A plus KQ2 over R2A. Right? You plug in the value and eventually you will get negative 3 times 10 to the power of 8 volt. So this is the final answer. Right? So I give you 1 minute to write it down. Okay, you yourself complete the substitutions right here and then see whether you can get the final answer or not. So remember, now you need to include the negative sign And that is the reason why you obtain a negative value right here. Okay, that's why you get a negative value right here. So negative 3 times 10 to the power of 8 volt. So I give you 1 minute to write it down. If you are done, then you can try example 6 first. Okay, kalau kamu dah siap, kamu boleh coba example 6. All right. So questions 5, it asks you to calculate total potential at one point. You have a system of 2 charge, so you calculate the potentials from the both of them. Now, how about questions example 6? So example 6, once again, now you have 2-point charges, one with a positive charge, one is a negative charge. They are being placed 0.1 meter apart. Point A is midway. Midway means halfway. The distance on the left is equal to the distance on the right between them. So point B is 0.08 meter from Q1 and 0.06 meter from Q2 as shown in the figure. So the question is being very nice to you. They give you this diagram already, okay? So you don't have to sketch your own diagram. So questions A asks you to calculate the electric potential at point A. Questions B asks you to calculate electric potential at point B. You are given 2 points in the questions, but that doesn't matter, not that important yet. For questions A and B, it's actually same as your example 5. You look at the questions. Now you have a system of 2 charges. Okay, you have a system of 2 charges. You don't care how many points is being mentioned in the questions. You look at the amounts of charge first. So you are given 2 charges, Q1 and Q2. Therefore, in order to calculate electric potential at point A, you need to add the potential from the both of them. So VA is equals to V1A plus V2A. All right, so you solve it and you should obtain negative 738 volt. All right, if you got it right, you should obtain negative 738. And then for questions B, once again, you don't have to look at all the other points. What you have to look at, you just focus on how many charges do you have in the system. So you have Q1, you have Q2. Therefore, for electric potential at point B, it is equals to V1B plus V2B. If you got it right, if you include the negative sign in your calculations, you got the right length, then you should obtain negative 708 volt. Sorry, negative 705, not 08, my bad. 705 volt. All right, so you should obtain both negative value, negative 738 volt and negative 705 volt. That is the potential at point A and at point B. Okay, the total potentials. So it doesn't matter how many points being mentioned. You just look at the amounts of charges you have right now in the system. So in this system, you have 2 charges. Therefore, you calculate the potential from the both of them. Okay, and then for a question, for point B again, you are looking at 2 charges, a system of 2 charges. So you just add up the potentials from both of them. So now I give you 2 minutes to solve these 2 questions, to calculate it. Okay, see whether you can get the right answer or not. Before we proceed to question C. Question C is slightly more complicated, but we can still do it. All right, so 2 minutes from now for you to solve questions A and B. If you have any questions, you may ask. Okay, boleh dapat jawapan tak?
Boleh, Madam.
Bagus. Right, so total potential actually is quite simple. You look at how many charges you have in one system, and then you calculate the potentials and you add them up. Okay, that is the meanings of algebraic sum in your notes. Okay, now question C. Okay, let's look at question C. Question C asks you to calculate work done. Okay, now you want to calculate W by the electric field on a test charge. So you are given a test charge, which is Q naught, that travels from point B to point A. So this is the key part. You want to calculate W, you are given Q naught, which means we can calculate W by using Q naught delta V. All right, delta V. Now, use delta V. Why? Because now your charge is no longer moving from infinity to a point inside the field. Now, what happens here is you're traveling from one point to the other point. So when you look at potential difference, the change in potential difference, okay, it is actually equals to Q naught V final minus V initial. Okay, V final minus V initial. Now, what does it mean by V final minus V initial? How do we know whether which one is final, which one is initial? You look at the questions again. Questions say now you're traveling from point B to point A. From B to A, meaning that point A is now your final position. Point B is now your initial position. Therefore, in order to calculate the work done in question C, W is equals to Q naught VA minus VB. All right, so this VA, you're using the total potential at point A. That's why you have questions A and B just now. Okay, questions A and B just now ask you to calculate total potential at point A and point B. And you have to use the answer. You have to use the total potentials right here to calculate the potential difference. Okay, so VA and VB, you have it right here. So VA is the final positions. Therefore, we are going to plug it into our questions, okay, into our solutions. So it is equals to 2.5 times 10 to the power negative 9, VA negative 738 minus VB also a negative value, so negative 705. You need to include the negative sign in your substitution. Right, you cannot simply use 738 minus 705. It should be negative 738 minus negative 705. So W is equals to negative 8.25 times 10 to the power of negative 8 joule. Okay, negative 8 joule. So this is how you calculate it. Now, this question is very nice to use again. Why? Because it gave you questions A and questions B. It guides you. Okay, it reminds you to calculate total potential first. But quite often, question won't ask you to calculate A and B. Straight away, it will ask you to calculate the work done by the electric field on a test charge that travel from point B to point A without telling you, without reminding you to calculate total potential first. So you yourself need to know, okay, in order to calculate the potential difference for work done, first you need to determine the total potential at point A first, and then determine the total potential at point B before you solve it. Alright, so kerap soalan tak akan guide kamu, okay, dia tak akan guide kamu. Dia akan terus suruh kamu cari work done. So Anda sendiri kena tahu, walaupun Anda nak guna delta V dalam pengiraan Anda, but this delta V, the final and initial, it should be the total potential at final position. Okay, this is a total potential, total V at final position. Tolak total V at initial position. Okay, total V at initial position. Right? So you are not looking at just one V, you are looking at total V between two given points. All right, so now again, I give you 2 minutes to write it down. So you make a bit of notes sendiri buat sikit catatan, okay, about the total V. All right, about the total V and the potential difference delta V. So sendiri buat sikit catatan supaya Anda tahu betul-betul faham. Okay, what is the difference between total and potential difference? So if you are done, you may try question 7 first. Okay, so I give you 2 minutes to write it down. Then you can try question 7. Okay, you can try question 7. All right. Okay, so example 7. So example 7, just now we're looking at work done. These questions we're going to look at energy, okay? Energy, there are 2 types of energy in terms of a potential energy difference and also the total potential energy. Now let us begin. 2-point charges, again you are given 2-point charge. So Q1 is a positive charge and again Q2 is a negative charge. They are placed 4 meter and 5 meter from point P respectively as shown in figure below. Calculate the electric potential P due to the charges. So again, you're being asked to calculate potential at point P. So meaning that you need to calculate the total potential because you have 2 charges in the system. So Vp is equals to V1P plus V2P. Okay, V1P plus V2P. So you calculate the total potential and you should obtain negative 6300 V if you got it right. Okay, kalau kamu kira dengan betul, Anda sepatutnya dapat negative 6300 V. So I give you 1 minute, see whether you can get the answer or not before we proceed to a new things in chapter 1. All right, now let's look at questions B. Questions B need to think a little bit. If the test charge moved from infinity to point P, determine the change in electric potential energy for this charge. Okay, that means the change in potential energy for this charge. So when we're looking at infinity, okay, from infinity, I'm going to explain a bit of concept first before we solve the questions, all right? So when we're looking at the charge from infinity, okay, from infinity, then we know U is equals to W, which is equals to Q naught over R, right? This is straight away from infinity. What if the question asks you to calculate the change in potential energy from two different positions? So if you're going to look at the change of potential energy from two different positions, let's say from a point A to point B, then what are we going to do? So from point A to point B, we know that is equals to WAB. And if you're going to look at the change in potential energy, then obviously it's going to be U final minus U initial. Okay, U final minus U initial. But at the same time, if you have WAB, okay, we also know that WAB, it is equals to Q naught delta V. That is what based on what we have learned before, right? So by combining these two equations, okay, by combining these two equations, actually we can come in the conclusions that delta U is also equals to Q naught delta V. Meaning that if you are given potential energy, final potential energy, and initial potential energy, or if you are given final and initial potential, then you can use it to calculate the other quantity, okay, the other variable. So V final minus V initial. So if you are given either one, then you can use it to calculate the other one. So this equation, it shows you the relationship between delta U and delta V. Okay, you can use delta V to deduce the values of delta U, and you can also use the values of delta U to deduce the values of delta V, right? So now let us try to use these equations in questions B. See, how are we going to apply this relationship in questions B? So according to questions B, now you want to look at the change in potential energy. Okay, potential energy from infinity to P, all right? So from infinity to P, meaning that now P is your final position and infinity is your initial position, all right? Initial position. Well, of course, you can straight away apply this equation. But what I want to show you right now, we want to learn how to use this equation. Okay, we want to learn how to use these equations. Okay, let's see. Oh, wait, yeah. Now let's see. How are we going to apply this one? Because the first one, actually, we cannot use it. We don't have the R. Okay, R is not given. Never mind. Let's see how to calculate this one. So if you want to apply this delta U equals to Q naught delta V, okay, we can expand these equations into Q naught. Now V final is P. So VP, my final position is P, so VP minus V infinity. Aha. So VP, actually, we already have it from questions 1. Questions 1, we already calculated the total potential at point P. Okay, therefore, it is equal to Q naught. Okay, Q naught, you plug in the value right here lah. And then VP negative 6300 minus, now how about V infinity? V infinity is equals to 0, right? It's at infinity. You don't even have to calculate it. Therefore, the final answer is equals to negative 1.89 times 10 to the power of negative 2 joule. Now let's see, how do I know V infinity is equals to 0? If V infinity, now let us go back to the question, okay, the original questions. Kalau kita tengok original questions. If you look at original questions, if your object, you're going to calculate the V at infinity, okay, so we're going to use V1 infinity plus V2 infinity. So it will be equals to KQ1 over R infinity plus KQ2 over R infinity. Anything divided by infinity is equal to 0. So basically it's just 0 plus 0. Therefore, V infinity is equal to 0. Right? Therefore, V infinity is equal to 0 because anything divided by infinity is 0. Okay, so that is how you solve it. Okay, that is how you solve it. Okay. So I give you 2 minutes to write it down. Okay, 2 minit bagi anda tulis. So if you want to use the first equations, okay, if you want to use these equations, can or cannot, yes, you can, but then you need to calculate the total energy lah. Okay, you need to calculate the total energy from infinity. So your U total, okay, will be equals to the U1, okay, U1 infinity, and then plus the, not U1 infinity, sorry, U1P, and then plus the U2P, okay, also can, okay, also can. But then this is, I don't encourage you to use this one, okay? I don't encourage you to use this one because it's a bit confusing when you combine it to the questions that involve 3 charges, okay? To the questions that involve 3 charges. Dia akan jadi sikit rumit. So I don't encourage you to use this one. Okay, so actually questions B in another works, okay, kalau nak betul-betul nak faham questions B, okay, because now you already have 2 charges in the system, you want to bring in the 3rd charge, the test charge. So this one is actually also equals to the potential energy needed, okay, to bring in 3rd charge. Right, to bring in the charge. That's why tadi saya kata kalau kamu nak kira dengan first equations, you have to use U 2 times. Okay, you have to use U1P plus U2P. Okay, U1P plus U2P. Kalau lah kamu nak guna U. Okay, U equals to U1P plus U2P. Okay, so Q1 Q naught over R1P plus KQ2 Q naught over R2P. If you truly want to use this one, okay, but it will be easier if you use the one in green color because you already calculate the VP in questions 8. Okay, so actually it has the same meanings lah. Change in potential energy with the potential energy needed to bring in 3rd charge because now this Q3 is the charge number 3 in our system. It's the 3rd charge that you want to add into the system. All right. So now let's look at question C. So question C shows you the main difference between charge needed to bring in the 3rd charge, the energy needed to bring in the 3rd charge, and the total energy for a system of 3 charges. So when charge Q3 is being placed at point P, so what you have right now is here is your first charge, negative charge Q1. And then you have a Q2 right here, is a positive charge. And then the third charge that you place in the system right now, it is also a positive charge, Q naught, okay, Q3. So now you have a system of 3 charges. Okay, so how are you going to calculate the U total? So U total is equals to, okay, is equals to KQ1 Q2 over R12 plus KQ1 Q3 over R13 plus KQ2 Q3 over R23. So this is the total energy in the system. Just now it's just the energy needed to bring in the third charge. Aha, so now you see the difference. So bila ada soalan, kita boleh nampak dengan lebih jelas. What is the difference between these two situations? Right, so you calculate it. If you got it right, then you should obtain U total. U total equals to negative 5.49 times 10 to the power of negative 2 joule. Okay, negative 5.49 times 10 to the power of negative 2 joule. All right, so I give you 2 minutes to complete the questions. Okay, 2 minutes to complete question C. It's just very simple. You just plug in everything and then press your calculator. You should get the answer. All right, just that you need to know how to determine the distance between 1 and 2. So you have a right angle triangle right here. Okay, so given here is 5 meter, and then given here is 4 meter. So the other side here, it should be 3 meter. Sendiri kira by using Pythagoras theorem. Okay, by using Pythagoras theorem, so you should be able to obtain here as 3 meter. Alright, so sendiri catat. Beberapa minit bagi Anda catat before we proceed to 1.4, the final subtopic. Okay, the final subtopic. So if you are done, what I want you to do, I want you to make a correction first, okay? Diagram in your example 8 and diagram in your example 10, they are terbalik, okay? So you need to change it, okay? You redraw it. Okay, gambar raja dalam example 8 dengan gambar raja dalam example 10, dia terbalik. So kalau kamu dah siap salin soalan ini, kamu buat pembetulan dulu dalam buku Anda. Okay, buat catatan ke atau nak lukis simulator pelang pada Anda. But make sure you know that the diagram in example 8 and the diagram in example 10, they are wrong. Okay, they are terbalik. Okay, boleh? Setakat ini ada apa-apa pertanyaan? Any questions before we proceed to the last final subtopic? Masih hidup gak kelas ini?
Ada, madam.
Oh, ada hidup lagi, bagus. Jangan tak hidup. Kalau kamu tak hidup, saya risau dah. Alright, so gambar raja example 8 and example 10 terbalik. Okay, make sure you correct it. This should be the right diagram for example 8. Alright, so if you look at the learning outcome 1.4, so use E equals to delta V over D for uniform electric field. So you have two plates. Okay, you have two plates. So the uniform electric field is happening in between the plate. All right, so the uniform inside it, or the electric field inside, they are all uniform. But then this is not the only equations that we're going to use in this chapter. Remember what I told you guys yesterday? You need to know how to solve projectile motions questions again in this subtopic. And we will go through one questions after this. See how to use projectile motions question, method solutions in this, okay, in this subtopic. Okay, let us begin with example 8. Okay, example 8. The particles with mass 5 milligram. Okay, now whenever you are given the mass, means that the weight is not negligible. You need to take into consideration the weight of the object. Okay, but if you are given electron, then you can neglect the weight in your calculation. Otherwise, you need to take into consideration the weight in your calculations. Okay, if you are given. So you are given the mass, okay, the particle with mass 5 mg and carries charge of 2 microcoulomb is held at rest. Now the keyword is at rest. You have just one charge and it is at rest. So it belongs to case number 1. Okay, where your object is stationary, not moving. Between two charged parallel metal plates as shown in the figure below. So now calculate the electric field strength between parallel plates. It asks you to calculate E. So we know E is equals to a delta V, but then can we use delta V here? No, because we are not given the delta V, and then we are not given D. Okay, kita tak ada D, D is unknown, V is also unknown. So obviously we cannot calculate E by using delta V over D. But what we do know, we are given a statement. Now this charge is at rest. If it is at rest, what does it mean? It means summations F is equals to 0. So now we try to link this concept to the diagram. If you look at the diagram, if it is stationary and you have a charge, we know that, well, this charge, it comes with a non-negligible weight. It has a weight that you need to take into consideration. But then the reasons why it remains stationary, it remains at rest, it is because there's another force acting in the opposite direction. And obviously this would be our electric force. So Fe minus W equals to 0. That is the reason why it remains static, because the net force acting on the charge is 0. If you rearrange the equation, then we know that Fe is equals to W. Fe, well, the electric force acting on a charge is QE. Okay, so QE equals to mg. QE equals to mg, Q not E. So E is equals to mg divided by Q naught. Right, so from here you can then determine the values of electric field, which is equals to 24.5 NC negative 1. Okay, 24.5 NC negative 1. Make sure the mass is in SI unit. Okay, the mass is in SI unit. So 5 mg is equals to 5 times 10 to the power of negative 3 gram. But gram is not SI unit. Therefore, it is equals to 5 times 10 to the power of negative 6 kg. All right, so kg is the one that we want to use in our calculation. This is a SI unit. So plug everything into the equations. You should obtain 24.5 NC negative 1. Next question. If the particles is moving upward with constant velocity, what would happen to the values of E? E remain constant. How do I know it remains constant? How do I know it remains constant? Because, okay, because summations F is still equals to 0. Okay, because summations F is still equals to 0. Therefore, E remain constant. Because M is a fixed, is the same. G is just a constant value. And Q naught, you're still looking at the same particles. Therefore, E is still 24.5 NC negative 1. All right. But if it is moving with an acceleration, then it will change. Alright, kalau dia bergerak dengan accelerations, then E kamu akan berubah. So berubah, bertambah atau berkurang, terpulang pada soalan. Right. So that is the answer for example 8. So I give you 2 minutes to write it down before we proceed to next question. So sendiri buat sedikit catatan untuk seorang explanation. Okay, untuk seorang explanation sendiri buat sedikit catatan. Okay, so example 8 is just a very simple, very short questions. Okay, as long as you don't make a careless mistake in the unit conversions, then most of you should be able to answer example 8. Now let's look at example 9. Example 9, an oil droplet of mass 3.3 times 10 to the power of negative 15 kg is released from rest in a uniform electric field produced by two parallel plates, separated 10 mm apart. The oil droplet then travels toward a positive plate with an acceleration of 4.5 times 10 to the power 15 ms negative 2 as shown in the figure. The parallel plates are connected to potentials of 1000 V. Calculate the charge on the droplet and state its sign. So now we want to calculate the charge. Okay, we want to calculate the charge. So which equation should we use here? Well, let's see. We have acceleration, we have a mass, okay, and then so we know the potential difference across the plate is 1000, and then we are given D. You have D, you have V, you can calculate E. Okay, so let's see what is the E first. So E equals to delta V over D. Delta V, now sometimes you have to check the diagram as well, 1000 and 0. So 1000 minus 0 divided by the D, which is a 10 mm, 10 times 10 to the power negative 3. So it is equals to 1 times 10 to the power of 5 V M negative 1. Right, so now we have E, and then we have M, we have A. So what should we do? Well, we have particles, a droplet moving with an acceleration. Therefore, we're going to apply Newton's second law here. So summations F equals to MA. Okay, summations F equals to MA. This question, it gives you a mass. Okay, so the weight is non-negligible. If the weight is non-negligible, means that it's going downward. W is going down. Okay, I'm going to change the color so that you can see it. W is going down. But then my object can move up. My oil droplet can move up. Why? That is because it experiences an attractive force. Okay, the electric force that pull it upward, which means my Fe is heading upwards. Okay, W is going down. Otherwise, if your Fe is also going downwards, then my object, my oil droplet would move downward. It won't be able to move upward. Okay? Kalau Fe saya ke bawah, W pun ke bawah, bermaksud oil droplet ini akan jatuh ke bawah. Dia tak akan bergerak ke atas. Tetapi sekarang kamu punya oil droplet ke atas, dan kita tahu weight mesti ke bawah. Therefore, Fe kita mesti 100% ke atas. Kalau tidak, oil droplet kamu tak akan dapat bergerak ke atas. So if you expand the equations, you will have Fe minus W equals to Ma. Okay, Fe minus W equals to Ma. Fe, well, electric force. So Q naught E minus Mg equals to Ma. Okay, so rearrange the equations. Now I'm just going to keep it. So Q naught is the charge that I want to determine. And then my E is 1 times 10 to the power of 5 minus M given is 3.3 times 10 to the power of negative 15 times 9.81 equals to 3.3 times 10 to the power of negative 15. And the expressions given 4.5 times 10 to the power of 15. Rearrange the equations, you should get Q naught equals to 1.49 times 10 to the power of negative 4 coulomb. Okay, and what type of charge it is? You look at the diagram again. This charge is being attracted towards positive plate. If it is being attracted toward positive plate, meaning that it is a negative charge. Okay, it is a negative charge. If you have a positive plate, okay, if you have a positive charge, then they will repel. Okay, they will repel. But if you have a positive plate and then with a negative charge, then they will attract. Okay, they will attract. So from here, I know that my charge, this oil droplet is a negative charge. Okay, this oil droplet is a negative charge. All right, so again, I give you 2 minutes to write it down, write down the solutions. Okay, if you want, you can also sketch this diagram so that you understand how do I determine, how do I know that this oil droplet is a negative charge. Okay, so 2 minutes for you to write it down before we proceed to final questions. If you are done, of course, you may try example 10 first. Okay, kamu boleh coba example 10 dulu kalau kamu nak. Kalau dah siap example 9. Okay, so dia tak susah, dia cuma perlu fikir sedikit. Okay, dia perlu fikir sedikit. So if you have something moving with constant velocity or at rest, remember summations F is equal to 0, you apply Newton's first law. If you have a particles moving with acceleration, then you apply Newton's second law. Okay, then you apply Newton's second law. So now let's see questions number 10, example number 10. This is a typical examples of a projectile motions in a uniform electric field in a parallel plates. So a beam of electron enters a uniform electric field with velocity 1.5 times 10 to the power 7 meter per second. So it's entering with an initial velocity 1.5 times 10 to the power 7 ms negative 1. Oh yeah, one more thing, yeah. One of the information is missing. Okay, in the diagram, it should tell you the length of the plate. Okay, the length of the plate, it should be a 6 cm. So the length of the plate is given 6 cm. Initial velocity 1.5 times 10 to the power of negative 7, 10 to the power of 7 meter per second between two parallel plates as shown in the figure above. So the reasons why it can enter horizontally, that is because it's entering with an initial velocity. So sketch the path of electron beams in the electric field and after emerging from electric field. So it's being deflected, but it won't enter the plate. Okay, it will be able to travel through the plate and exit and emerge and come out from the plate. All right. So sometimes, sometimes it might not have enough speed, enough energy to travel through the plate. Okay, it will be deflected toward positive plate and then being absorbed by the plate. But according to these questions, now you have an electron beam that is able to travel through the plate. Okay, and it is able to emerge from the electric field. So this is an electron. Okay, now you have a negative charge. Negative charge enter electric field. So it will be attracted towards positive plate. Okay, it will be deflected toward positive plate. So it will be deflected toward positive plate. But then what happens right here? Okay, it deflect, curve a bit. Cannot. So it deflect, curve, and then when it reaches this dotted line, after it passes through this dotted line, it's no longer a curved shape. What happens right here? It is a straight line. Okay, it is a straight line. So you need to sketch the diagram. Okay, sketch the path. That here is a curved line, and then here you draw it with a ruler. Okay, after it exits from the plate, after it passes through this dotted line, okay, you use a ruler to draw it. Okay, you draw with a ruler. So to show that it is a straight line. So now the question asks you to explain the shape of the path. So how are you going to explain the shape? You explain in terms of in between the plate. Okay, in between the plates or inside electric field. Okay, in between the plates and outside the electric field or outside the plate. Okay, outside the plate or outside electric field. So in between the plate, what happens to the path? The path, the shape of the path is parabolic path. Okay, parabolic path. Why? Because it asks you to explain. So you need to tell it why. Because electron is being deflected. Okay, deflected towards where? Towards positive plate. Why? Okay, why is it being deflected? Due to electric force. Right? Due to electric force. So you explain the shape, you explain why it moved. It moved because of the force, because of electric force. And what happens outside electric field or outside the plate? It is a straight path. Okay, so why straight path? Because no force. Okay, because no force acting on the electron. Okay, no force acting on the electron. So that's it. Okay, that is how you explain the shape. You tell the reader what is the shape first, and then you explain why. Why is it a parabolic shape? Why is it a straight path, straight line shape? Okay. So now you have two questions. Okay, questions A, questions B done. So question C. Okay, so I give you 1 minute to write it down. If you're done, you can try question C first. Oke, kamu boleh coba soalan C dulu kalau Anda dah siap. Ini kalau Anda dah siap. So, masa Anda catat, saya buat semula diagram dia dulu. Oke, Anda catat dulu. Kalau ada soalan boleh tanya. All right. So last questions. Okay, last questions. Let's see. Question C. So you're looking at the same question, same plate. So two parallel plates now, they are set at a distance of 15 mm apart. So just now, original question, it just gives you the length of the plate. Now it tells you these two plates, they are located, which means that D is equals to 15 mm apart. Okay, and then the top potential, it is just now, it tells you it's positive. Now it tells you it is positive 200 volt. And then the bottom plate is a negative 200 volt. Okay, so one positive, one negative. Determines the magnitudes of the accelerations of electrons. So electron, usually we neglect the weight. Okay, we neglect the weight in our calculations because the weight is very, very, very small. So how are we going to calculate the accelerations? Well, it tells you accelerations, obviously, it means that you're going to apply Newton's second law. So summations F equals to ma. How are we going to expand it? Well, electron. Now, if you look at this type of question, when it enters the plate, since it will be deflected, you will have a horizontal projectile motions. Okay, what happens in a horizontal projectile motion? Let's see. In a horizontal projectile motions, we assume x component, it comes with constant v, and then a equals to 0, ax equals to 0. Whereas for y component, okay, for y component, it's moving with constant a. Meaning that now, if you want to determine the accelerations, you're just going to look at y components. Okay, you look at what happens along the y component. So summations F equals to ma. When your object is located in between the plate, the force acting on the charged particle is just a Fe. So Fe is equals to ma. Okay, we look at ma, a along vertical components, along y component. So Fe equals to ma. In that case, we have Q naught E equals to ma, right? So if you rearrange the equations, you will have A equals to Q naught E over M. So this is the equations that we're going to use in questions 1. But now we don't have E yet. So how are we going to calculate E? If you look at the questions, we are given the V. Okay, we have V on the two plates, and then we have the D. All right, we have the D. Initial position is a negative plate. It travels towards positive plate. So now we have E equals to delta V over D. Delta V, negative 200. Okay, it starts from negative 200. Or wait, we use positive 200 because we just want to find the difference. Okay, so we want to calculate delta V over D. So it is equals to 200 minus negative 200 over D. Okay, over D, the distance between them, 15 times 10 to the power of negative 3. So it is equals to 2.67 times 10 to the power of 4 Vm negative 1. Okay, it travels from here to here. So this is your final, this is your initial. So 200 minus negative 200, you obtain 400. 400 divided by 15 mm, you will get 2.67 times 10 to the power 4 Vm negative 1. You can then apply the equations to calculate the accelerations. So A is equals to, now Q naught, now you have electron. Electron is elementary charge. Okay, it's elementary charge. So you can get the value from the list of constant. So E is equals to, Q naught is equals to 1.6 times 10 to the power of negative 19. Electric field I have right now 2.67 times 10 to the power of 4 divided by the mass of electron, which is, you can get it from the list of a constant again, 9.11 times 10 to the power of negative 31. So A is equals to 4.69 times 10 to the power of 15 ms negative 2. So this is the answer, right? This is the answer. So this is how you solve it. All right, you start from looking at the diagram and see what is the information that you can get. And since you want to calculate accelerations, means that you're just going to look at the vertical component. Okay, what happens along the vertical path? Because accelerations, you have it only along the y component. So along the vertical components, you have just the electric force. Therefore, Fe equals to ma. Okay, Fe equals to ma. So Q naught E equals to ma. Rearrange the equations, and eventually you will get A equals to 4.69 times 10 to the power 15. Okay, so you write it down first. I give you 1 minute. After you're done, then okay, then we can proceed. Okay, we can proceed to the next one. All right, now let's look at the last question. So last question, calculate the speed. So question, okay, question asking for the speed. Okay, question asking for the speed. Speed means that you need to take into consideration both the directions and also the x component and also the y component. So the speed as it leaves the regions, okay, as it leaves the regions between the plate. Now let us go back to the original diagram. If you look at the diagram just now, the way you sketch the path, if you look at here, after it emerged, it is emerging at an angle. Okay, so this is x component, this is y component. So if you want to calculate the speed, meaning that you have to take into considerations both components. So you need to calculate Vx and Vy. All right, you need to calculate Vx and Vy. So let us see. Vx, well, when it comes to horizontal projectile motion, we know that it's moving with constant v. Therefore, Vx is equals to Ux, it is equals to 1.5 times 10 to the power of ms negative 1. So done. How about Vy? Vy, we don't have enough information yet. If you look at the information that we have right now, we have Ay equals to, well, from previous question, 4.69 times 10 to the power 15, ms negative 2. And then what else do we have? Well, it is a horizontal projectile motion, meaning that Uy is equals to 0. Okay, so we have Uy equals to 0 ms negative 1. That's it. Well, we don't have the Sy. Now, remember, when it comes to this question, Sy is not equals to D. All right, it's very important. Why? Again, let us go back to the original diagram. If you look at the original diagram, D, it represents the distance between two plates. Okay, it represents the distance between two plates. Sy is only equals to D if it is coming out from your negative plate. But now it's not. It's coming from outside. Okay, it is coming from outside here. And you don't know where is it entered from. Okay, it could be at the midpoint, midway between two plates. It could be slightly above midway. It could be slightly below midway, or it could be very close to a negative plate or close to a positive plate. You don't know. You don't know where is it. You don't know the exact positions along the y component. Therefore, you cannot say Sy equals to D. Okay, you cannot say Sy equals to D. It is not equals to D, so we don't have the information. So how about time? Do we have time? Well, we don't have it, but what we can do, we can calculate time from x component. When it comes to x component, because our object is moving with constant v, therefore we have only one equation, which is Sx equals to uxt. Rearrange equation, t is equals to Sx over ux. We are given 6 cm in the questions. Okay, 6 cm, how do I know? Because it's in between the plate. Because now you want to see what happens in between the plate. All right, so we have an Sx, the time taken for it to travel from the beginning of the plate until the end of the plate. So it is equals to 0.06 divided by 1.5 times 10 to the power of 10 to the power of 7. Okay, it's 7. So time taken for it to travel from the beginning of the plate until the end of the plate is 4 times 10 to the power of negative 9 seconds. It's very fast. Okay, it's traveling at a very high speed. So t equals to 4.9 and 4 times 10 to the power of negative 9 seconds. Now that you have A, you have U, you have T, you want to find V, you can then apply the 4 linear equation. So Vy is equals to Uy plus Ayt. This equals to 0 plus 4.69 times 10 to the power of 15 times 4 times 10 to the power of negative 9. So Vy is equal to 18.76 ms negative 1. Oh, sorry, not 18.76 times 10 to the power of 6 ms negative 1. Right. So now that you have Vx, you have Vy, you can then proceed to calculate V total, okay, your V. V equals to square root Vx squared plus Vy squared, okay, your V resultant. If you got it right, you should obtain 24 times 10 to the power of 6 ms negative 1. So this is the final answer. Do you have to determine the directions? No, you don't need to. Why? Because speed is a scalar quantity. Okay, if it is a scalar quantity, meaning that you don't need to state the direction. Okay, you don't need to calculate the direction. So done. If you got the speed 24 times 10 to the power of 6 meters per second, then that marks the end of this question. And that marks the end of today's class. So if you have any questions, you may ask. If no, that's all for today, and you may leave the class now. Thank you.